Hey, hi students. So today we are going to discuss on very important topic to very good understanding level. So if you guys feel if your friends are lagging this kind of knowledge, please share this video and make them to watch it, and you guys share your knowledge among yourself. So last class we discussed detail about the intrinsic semiconductor. So why we need actually intrinsic semiconductor, extrinsic semiconductor? The last class I given you a hint that if in order to increase the inert and intrinsic semiconductor, we need to increase the temperature. So for an example, if we are getting 1 milliamps of current for 300 Kelvin of temperature, we are getting this in semiconductor. If we need to get an expectation of 10 milliamps of current, then what we can do is that we can simply increase the temperature. That is the one thing we last class discussed. But without increasing this temperature, what we can do is that the simple process of doping can do this. So without increasing the temperature, here we are getting 1 milliamps for 300 Kelvin, which is intrinsic semiconductor. We can get the 10 milliamps for the same 300 Kelvin. This is with the extrinsic semiconductor. So how this is happening? So that's what we are going to discuss. So this is with the extrinsic and this is intrinsic. Okay. So let's take a simple silicon lattice structure. So for an example, let's take an n-type material. So we are going to take the pentavalent atom here. So pentavalent atom's best example is the phosphorus. So what's phosphorus outer shell is that 5 electron it will have. So let's mention like this. Then it is surrounded by silicon. It's in 3D lattice, but I am mentioning it in a 2D for you guys to understand. So let's take consideration of each individual electron. It will have its 4 electrons in the outer shell. It will again phosphorus will be there. So like this, it will be 3D structure. But for our understanding, let's take a simple small topo from here. So what will happen? Here there will be a covalent bond formation. So every atom in a silicon will form covalent bond, not ionic bond. So there will be a covalent bond between these two pairs. So this is how the covalent bond structure will be. Here you see, here there is one free electron. An electron is free. So what this will happen? This free electron will be ready to contribute it to outermost shell. So here the doping with pentavalent atom results in n-type material. So this will result in a state of availability for electron in a state higher than normal valence band. So let's take here we are going to discuss about the band only, not a single structure. So it's a band. So if you take this, so this is conduction band. So this is conduction band and this is valence band. Now what will happen? This electron is available here, right? So that electron will be readily available here itself. So there is a change of state here. So that we will be representing as a ED, that is a donor energy level. So that is a donor energy level. So the electron will be available here. So here there is no need for the 300K temperature. Even at the room temperature like 50 or 100, in those time of temperature itself, this electron can easily move into this conduction band and there will be a contribution of IN. So that is what will happen. For an example, let's take a case in silicon or germanium. For in silicon, what it will happen is that even for 100K temperature, it will be jumping into the higher level and it will produce the current. In case of germanium, even 50K temperature is enough for him to move this electron from here to here. Not 300K kind of temperature is not needed. So even in the room temperature, it is possible. So the simple thing that we have to take into picture is that when an pentavalent atom is replaced in an silicon lattice structure, the pentavalent atom which is coming into silicon lattice, that is called doping. The process is called doping. Once the doping is done, there will be a free electrons. In case of here there is a free electrons. In case if we had that trivalent atom, there will be a free holes. So this electron is readily available. So even at the room temperature, these free electrons can easily jump into condension band. In room temperature, electron can jump to the condension band. So then what will happen? The IN will increases. The contribution of IN will increases. That will directly increases the I net. So this is it's an N-type material, right? So the majority charge carrier will be of electrons. So the holes will also be there because not all the thing in the world is ideal. So there will be slight amount of IP, but that will not be that much. That is a minority charge carrier consideration. So the thing is that at 300 Kelvin, all these impurity atoms become ion and there is impurely ionized. At 300 Kelvin, the bond to bond transition and electron hole parallel will take place. So in N-type semiconductor, electrons are majority charge carriers and holes are minority charge carrier. The thing that we discuss here is that N will be greater than P because of this kind of thing. Because the free electrons is available. The fifth electron in the pentavalent atom will be the free electron. I hope this is get is understood for you. I think this structure will give you some quite understanding. So this free electron is the key for all the thing. Okay, so next class let's discuss about the p-type. So let's draw one lattice structure for p-type with a trivalent atom. Then you will be getting know about the effect of majority charge carrier of that is holes in the p-type material. The same thing here is happening there. So I hope this give you a good understanding. I think this is how the N-type, P-type materials are being categorized and how the current movement produced here coming into picture. I hope this is good for you. So even if you guys have any doubt, please ping in the comment section. I will for sure clear it. So like, share and subscribe the channel. It will be get motivated for me to take more and more deeper into the other subjects and these concepts. Thank you.